Welcome. In this video, we are going to be looking at section 3.5. This is integration by parts. And our objective for this video is going to be just to walk through finding the antiderivative using this technique we'll call the by parts technique. So at the beginning of this video, let's just take a look at the definition of kind of this integration by parts technique. It's going to be using u's and v's, but it's going to be a little bit different than our u substitution that we did in our last section. So we want to make sure we have a kind of a different category for these types of integrals. So this technique is going to be based off of finding a u function and finding a dv function. And by definition, this will result in a uv product minus a new integral of v du. So we're going to consider both u and v as two functions of x, and dv and du are the derivatives of those two functions. So just to give some background on why this all works out, just consider the idea of the product rule. So we know that if we take a derivative ddx of some function u times some other function v, we can know that that is equal to the following. It's equal to the first function's derivative u prime times v added to u v prime. So that's our product rule of two functions using those two variables u and v. Now let's go ahead and just consider rewriting this just a little bit in terms of some notation that we're working with our v and u. This would be the same thing here as, again, the derivative with respect to an x variable of a u function times a v. And we can rewrite this as v du, or the derivative of the u function, plus u times dv, just to get our same notation here. If we consider taking an integral of this setup of both sides, we can consider, really there's kind of three integrals if we want to piece these out because we're just taking a sum. We can consider that the integral of a derivative dx is just going to become just the u times v product. The integral of the v function du here, we can give here as just this integral itself. So we can bring that down, the integral of v du plus the integral of u dv, or those two products. Now, if we go to just rewrite this structure here, we can consider this as the integral of u dv. We know what that is in our notation here. That's the first item in our integration by parts. And that's sitting right here. If we choose to solve for that, we can consider the u times v, and we can subtract the second integral, the u dv integral, and leave behind our integral of v du. So you'll notice that this definition here is the exact same that we get for this integration by parts. So when we do this integration by parts, this is really just maybe undoing or our product rule. So if I consider the product rule, we're just kind of undoing that product rule by this new technique of integration by parts. So undoing maybe the product rule there. Okay, so there's just some background of why this is being used. So let's go ahead and see if we can start to work with this definition. So let's go ahead and for the integral x e to the x dx. The beginning stages of this technique are going to be requiring a u function and a dv function. That's what we want to house inside of our original integral here. So some techniques or maybe some tips of what is a good u function and what is a dv function would be, I want a u function that I can take a derivative, and I want that derivative to be simplified or a more simple function to work with. I want to take a dv possibly that has an antiderivative that also simplifies if possible. So in this case, where we have really two functions of x, we have the x and the e to the x term to consider. Well, one of these is going to have to be the u, and one of them is going to have to be the dv. So if I considered here u as just the single x term, this would give me a du, or derivative of that u function, of just 1 dx, which is certainly simplified. It's practically simplified to as much as we can. This would force our dv function to be the remaining e to the x and then dx. So we don't want to forget that portion. This dx would go along with our dv function there. So now I want to take an antiderivative of that same function. So if I want to take an antiderivative, I become a v function. That antiderivative of e to the x is simply just e to the x. So I've kind of got my setup here, all four functions that I need, the original u and dv, and then my du and my v function. So now I'm going to go ahead and try to replicate again the solution to our problem, or the alternative integral. And that's the uv product. So I like to kind of use some arrows to remind myself where the products are. You can take the uv product, and I'll just write it down again generically here below. And then we're going to take the integral of v du, which again would be kind of an arrow right across. And as long as we set it up just like this, we can again kind of remember that same pattern. We're going to take a uv product, v du as our integral. So let's go ahead and fill in the details for this specific integral. We're going to have, again, the uv product for us would just be x times e to the x. And then we're going to subtract the integral of e to the x dx. So we're taking our v du. Okay, so one portion of this is outside the integral and doesn't have to be changed. And our last portion here is part of an integral, so we'll have to evaluate its antiderivative. So we get to keep x e to the x here. Subtract the antiderivative of e to the x is still e to the x itself. No change. And like all antiderivatives here, we need to, again, attach that plus c. So this gives us our final result of our integral of x times e raised to the x power. So that's our first integral by using the integration by parts. Let's go ahead and take a look at the second one here. This one also has an exponential term to consider. we have 2 plus 5x times e raised to the x over 3. So again, when I'm taking a look at using integration by parts, I always want to consider first, again, what is my u function and what is the dv function going to be? I'm considering first my u function. I want some function that will simplify as I take its derivative. So for this one, it looks like the value that it'll probably simplify the best when it takes its derivative would be the 2 plus 5x. The remaining portion, which is the e raised to the x over 3 dx, will become that dv function. Okay, so now I get to go through and solve for what is my du function. The derivative of the u function here will just have, looks like, a derivative of 5 and then dx. So make sure that we have that attached, 5 dx. The v function would be the antiderivative of my dv. So if I'm taking an antiderivative of this e raised to the x over 3, well, exponentials, again, are its own antiderivative. So we could start with e raised to the x over 3. But notice that the function of x inside that exponent is not just x itself. It's x over 3. So usually when I would take the derivative of this term, just to go back, I would consider this as really 1/3 x. And so when I take its derivative, I would repeat my function times the derivative of the exponent, which is 1/3. Now, we want to do the opposite here while taking an antiderivative. So if I consider kind of going in reverse, notice that if I kind of go back the other way, well, the opposite of multiplying by 1/3 would be dividing by 1/3 or multiplying by a constant 3. So notice that this value is 1/3 of its original. And so when I go into the reverse order, I need to actually multiply by that 3 instead of divide by that 3. And so for that reasoning there, this antiderivative becomes just 3e raised to the x over 3. And if you try taking your derivative of this new v function, you should find that that results in your original dv. So you can take a moment if you'd like to double check that work as well. So let's go ahead and look at our integration by parts. This would be, again, the u v product minus the integral of v du. So I'm going to use, again, the arrows to kind of visualize our products here. First, the uv product. We've got u, and then the v. And then we're going to subtract the integral of v du, which is here 5 dx. Okay, let's go ahead and maybe simplify this just a little bit. I'm going to go ahead and, just for cleaning this up, I'm going to take this 3 and distribute it. So we have 6 plus 15x times the exponential. Subtract. It looks like I have a couple constants here that I can combine, and I'm going to pull those outside the integral. So I have 15 integral of e raised to the x over 3 times dx. Now, notice what we have here in my remaining integral. This is the same function that we started with in our dv function, right here. And we actually found its antiderivative to be 3 times e raised to the x over 3. So I can actually use that result and say, well, this component here, this is just going to be, again, 3e raised x to the x over 3. That's what that component's going to have to be. So when I rewrite this integral, I could rewrite this the following. The first portion is unchanged. We can rewrite it. Now, I already had that constant of 15, and I'm going to be multiplying a constant of 3. So we get negative 45, negative 45, times, again, that exponential e raised to the x over 3. And then as we do for all our antiderivatives here, we need to put this plus constant c on the end. And we will leave this as our complete solution. So there's kind of a nice little pattern here where that same dv function pops up in the secondary integral that we're taking. So that can be helpful. Let's go ahead and jump into another question. This one involves a natural log function. So first two had a exponential. Now we're going to look at natural log. So again, we have really two functions of x here, x raised to the third power, and we also have an x raised, or a natural log function at least. So first, I'm going to consider, well, what would be my best u and dv function? Make some space, dv function. So first, I want to consider, well, which one of these do I even know the derivative for? So I know the derivative for x to the third, and I certainly know the derivative for natural log would be 1 over x. So both of those seem like they're simplifying in a way. If I wanted to consider, well, the dv is something I need to know its antiderivative. So I know the antiderivative of x to the third. I can find that with a power rule. But the antiderivative for the natural log, that's going to be a little trickier. I'm not quite sure what that is off the top of our mind, at least. And I don't think we've learned that rule yet. So my recommendation is let's go ahead and use the natural log as our function of u, because I know its derivative. And I know the antiderivative for the x to the third power, dx. So kind of as process of elimination here, I think this would be the best arrangement for our two functions. So if we wanted to go ahead and group the dx, that's going to be part of that x to the third power. Okay, so I've accounted for everything inside that integral with the u and the dv function. Now let's go ahead and try to find my du, the derivative, and then my antiderivative v function. So we just stated earlier that the derivative of the natural log was 1 over x, and then dx. And then we could do antiderivative for x to the third power. So this would be x raised to the fourth, raise the power by 1, divided by 4. And that would be left there. All right, again, just as a reminder, our equation is used as u times v minus the integral of v du. So again, you can use your arrows to work this out. So we got the uv product minus the integral of v du. So let's go ahead and take those. I'm going to kind of work this on the side. My uv product would be I'll put this x to the fourth over 4 times the natural log of x. Then we'll have the subtraction of the integral of here. Notice that we have v du, and looks like we have 1 over x, x to the 4th over 4. If we combine these as a product right off the bat, I think we're going to be losing one of the x's here. And so this v du product, if we want to do that really quick on the side here, would have to work out as x to the 3rd, because we're going to lose one of those x powers from that denominator, cancellation, and then divided by 4. So one of those would kind of cancel those there. And that's going to be dx. So let's go ahead and jot that in. We have x to the 3rd divided by 4 dx. Now we can consider taking another antiderivative with what we have left here. So we have x raised to the 4th over 4 times the natural log of x. And then if we want, you can pull out the negative 1/4 and integrate x to the 3rd dx here. And that will become the following. We have x to the 4th over 4 times the natural log of x minus, well, we have 1/4 here, and the antiderivative for x to the 3rd becomes x to the 4th over 4. So we're really going to have x to the 4th over 4 with that, multiplied by another 4th will end up giving me 1 over 16 times x to the 4th that remains. And then again, we need a plus constant c. And that would complete that, antiderivative. There we go. So that's that component there. All right, so that's working with two functions of x, including that natural log function. Part D takes a look at just the natural log. Well, so this one's an interesting one. We said in our previous problem that we didn't know the antiderivative for the natural log function. So here is where we actually are going to be able to find that. So here we only have one function of x to work with. So when we consider the v and the du function, well, there's really only one option for v, and that happens to be the ln function. So we're going to have to use the natural log of x for that v function. Or sorry, we should have a u and dv. So we'll have that as a u function. There we go. So we've got our u function. dv is simply going to have to just take dx. There's only that differential back. So we have u as the natural log. That would mean that du is 1 over x dx. We've seen that before. If our dv is just simply dx, that means if I go to my v function, that will just give me an antiderivative from 1. That antiderivative is just going to be x itself. So I have my derivative of u and my antiderivative of dv. Now we can follow through with our rule. So we're going to have the uv product minus the integral of v du. So let's get after that result. We have the integral of the natural log of x times x itself. Sometimes we'll move that x in the opposite order, so that might be helpful. Just x times the natural log of x minus the integral of x over times 1 over x dx, or v du. Notice that in our integral here, some x's will cancel out, so we'll just be left with the integral of 1 dx. That happens to be, again, that same antiderivative we just took. And so the antiderivative of just 1 is going to be our variable x. So we have x times natural log of x minus x itself will be my antiderivative of 1. And then we can do our plus constant c. So we've got, this is as a pretty good, nice result for us, that the natural log's antiderivative is just x times itself, natural log of x, subtract x plus c. Let's keep that in mind for later on. We'll definitely use this result as we move forward. So this is a powerful result that can help us in the subsequent problems. All right, let's go ahead and take a look at part E. We have the integral from 2 to 5 of 7x divided by 4x plus 3 dx. So taking a look at this one, this looks like very similar to something that we worked on in our last class period or last video, where we used a u substitution. So we're going to be given an opportunity to use both of these techniques as we go and move along. So I might go ahead and try to kind of revert back to our u substitution here and see if this would be a good candidate. So let's go ahead and consider this underneath a, again, u sub technique. There we go. So based on the u sub, again, we would want to get both a u and a du function to cover the whole integral here. So one option that we could take here is to consider the denominator function 4x plus 3 as our u sub. This would give us a derivative of 4 dx. And we're not too far away from what we need. It looks like we have, if we're covering our bases here, we've got our 4x plus 3 covered. We do have that dx covered as well. And we need to cover, again, kind of some constants a little bit. Not too worried about that, but we do have this extra variable x in the numerator to cover. So if we consider how we would do that, I think one technique that we used at the end of our last video was to consider solving for x from that u substitution equation. So let's go ahead and try to do that. If I go to solve for u in this equation, I could say that we have, subtracting this equation by 3 on both sides, we have u minus 3 is equal to 4x. Therefore, we have u minus 3 divided by 4 is equal to x itself. So here we have a representation for x in terms of u that we can work with. So let's go ahead and isolate those terms that we have so far. Again, I'm going to kind of keep these bounds clean until I change these, because when we're using u substitution, it's most helpful to, again, change these bounds when I change these functions of x, or functions of x. One other adjustment that we can make before going through here is just isolate this dx term again. If I isolate dx by dividing by 4 on both sides, we'll notice that the dx here is just going to be the du divided by 4, or 1/4 times du. So let's go ahead and rewrite this. We have the integral of, we have that 7 that can kind of just keep inside that integral, that's okay. Divided by, we have the u itself, that's the 4x plus 3. And so we've got that as just a u. We also have that x variable that we highlighted in yellow. This x variable, we know its definition here as u minus 3 divided by 4. So we have u minus 3 divided by 4. And then finally, the du function here is going to be 1/4 times, or the dx here is 1/4 times du. So maybe give that a different color here as we go. So this is the dx that we're replacing right here would be, again, 1/4 times the du. Okay, so we got a lot of pieces going on here. So let's see if we can kind of work with simplifying this integral, and then we'll also want to consider the bounds. So I'm going to get to kind of simplifying this integral a little bit in terms of this function. So we've got the integral here. We have 7 and 4, and then we're also dividing by 4 out here as well. So if I take all of those constants, I have 7 in the numerator, 4 in the denominator, and another 1/4. So we take all those out as 7/16. And then we can consider if those are all kind of taken outside the integral, we really have u minus 3 divided by this other u. So this really becomes just u over u, or 1, minus 3 divided by u. And then you can keep that as just du on the outside. So there we go. So that would be my kind of simplified integral. Now I can go ahead and consider these bounds. When we consider the bounds, I'm again going to take a look at this original relationship with u and x. I want to know where the bounds are at x equals 2 and x equals 5. So let's start with that 2. When x is equal to 2, my u is going to be 4 times 2 plus 3, or 11. So that's going to be my lower bound. And then when x is equal to 5, we can take the u as 4 times 5 plus 3, or 21, or 23, excuse me, 23. So I've got my upper bound of 23. All right, so let's go ahead and maybe move this just a bit. And we'll go ahead and consider kind of working out this rest of this integral. I'm going to rewrite it here on the side. Ran out of space here, so we have, let's just rewrite exactly what we have here. We have 7/16, and then we have our integral of 1 minus 3 over u du. Again, with those bounds of 11 and 23. All right, so let's take our antiderivatives here. That 7/16 can be kept outside. My integral for, or antiderivative for both of these terms, first with 1, is just going to give me a u. And then minus, we have 3 over u, which is really going to be 3 times 1 over u. And 1 over u, its antiderivative, is going to be that natural log of u. So we can say that's minus 3 times the natural log of absolute value u. So this is our antiderivative in terms of u, which is looking pretty good for us. Now I just want to finish this off by, again, evaluating this antiderivative at my two endpoints to 23 and 11. And for this one, since we have some natural logs, I'll just kind of keep these in terms of that natural log for this portion. We're going to have the following, 7 over 16. We can, again, evaluate straight into our u. We'll have 23 minus ln of the absolute value 23, which is still positive, so we can just take 23. And then subtract the result, again, 7/16 times, we'll have 11, and then minus 3 natural log of 11. If you're going to work this out to an approximate solution, if that's needed for our problem, we can definitely do that. This will give us an approximate solution here of about 4.28 if you go out to 2 decimal places. Or you can, again, just keep with our current setup here. So that would be our, again, review for the u substitution with that extra variable. So you have kind of those 3 substitutions with the definite integral. Part F, let's go ahead and consider that one together. This one's also takes a little bit of algebra review to just consider how we want to break this integral down. We have the integral of 8 times the natural log of 6x squared inside dx. So one way we can get started with this process is just to consider 8 here is just a constant. And so you could rewrite this integral with 8 on the exterior or on the outside of this integral. And then we have natural log of 6x squared dx. Now, there's a couple ways we can go from here, and I'm going to kind of go a route of some natural log properties. So one property that we know from algebra is that we can take our natural logs and separate them with a product rule. So I can rewrite this integral as the following. 8 is on the outside. We have the integral of 2 terms. We'll have the natural log of 6 plus the natural log of what remains here, x squared dx. So we can transform that product of terms in the natural log with a sum. So that's the product rule of natural logs. The next thing that we can do is we can go one step further and utilize the power rule for natural logs. Notice that we have an x squared inside the second natural log, and we can use that power rule to bring 2 out as a constant multiple. And that's what we'll do in the next step. So we have 8 integral of the natural log of 6 plus we have 2 natural log of x. And that's dx. All right, so let's go ahead and we'll consider next how we would take the antiderivative of now these 2 remaining terms. So we can start with, again, that constant 8. We're going to keep that coming along. The natural log of 6 term is a constant itself, and so when it's inside that integral, we want to take the integral dx. We can attach, again, here a natural log of 6 times x. So we'll have natural log of 6 times x. And again, if you want You can do a little bracket there just to make sure it's not confused with the x outside. Next, we can take a look at the second term. We have plus. We'll do this in a different color here. This component here, 2, will remain. And then we have the natural log of x. Well, the antiderivative of natural log of x, I think we solved that in a previous problem. So let's just take a peek back up a couple problems. We found in part D that our integral of ln of x was b x times natural log of x minus x plus c. So I'm going to go ahead and use that result here. This is a great way to use that result and give this result to this portion of the problem. So we have 2 times, this is the x times the natural log of x minus x. We'll take that parenthesis for that single term. And then again, for the complete term here, we can again just add some constant plus c at the very end. And this would work for our final result. If you do want to distribute that 8 into the parenthesis, that works totally fine, but you don't necessarily have to. I'll go ahead and just simplify this to kind of give the final result here. If I distribute 8 really into a couple places here, we have 8 times the natural log of 6 times x. If I distribute this here, this really just becomes a 16, and that 16 can be distributed to a couple places as well. So we have plus 16, both of the x ln x, and the 16 will go to the x as well. Notice that if I distribute any constant here, this 8 distributed to just a constant plus c, it doesn't change this constant at the very end here. So when we're done with this, we can actually just leave this as just, again, a plus c. It's just going to be a different plus c, but we don't have to necessarily change that to anything. So that would be our final result if you wanted to have a distributed version. And that would be our result. So a couple of rules here. Again, we had the product rule for the natural log, and we use the power rule as well for that natural log in the next step. All right. Let's go ahead and keep rolling around here. We'll have part G. Part G is up next. All right, so when I consider part G, again, this is another definite integral that we can consider. We have the integral from 0 to 3 of 2x times e raised to the x plus 4. All right. And one way we can consider this e raised to the x plus 4 is to use a little exponential rule just to rewrite this. So the product rule, again, for the exponent here, can be used to help simplify this integral down just a little bit. So we have the integral of 0 to 3. We have the 2x. And then when I look at e raised to the x plus 4, I can actually rewrite this as two exponentials. One is e raised to the x, and the other one is multiplying e raised to the 4th power. So that is taking that sum in the exponent and separating that as a product of exponentials. Now, e to the 4th itself is just a constant term. So when I go to rewrite this a second time, I can kind of divide this out into really two portions. One is just the 2, and one's the e raised to the x. So this 2 and e to the x, e to the fourth, excuse me, can be brought out as constants. And then we have a new integral from 0 to 3 of x e raised to the x dx. Now, this is a very similar integral that we already solved in this class period. And so I'm going to go ahead and utilize that result. If you want, you can run through this again, and if you wanted to pause the video. But I'll go ahead and use the previous result again from the first part of this lesson. So if you want to pause and try this integral out again, you can. I'm going to go ahead and use that result that we had from before. So if you end up using the result from the first problem that we worked through in class, we can see that the integral for x e to the x was given as x e to the x minus e to the x. So I'm using that result, and we're going to consider, again, evaluating this from 0 to 3. So the first evaluation, again, at 3, this would be kind of like our capital F of 3, is that function evaluated at 3. So we get 3e raised to the third minus e raised to the third again. And then for the second component, subtracting f of 0, capital F of 0, would give us 0 times e to the 0 minus e to the 0. So looking at the parentheses here, this component goes to 0, and then minus e to the 0 is 1. So this whole second bit will just have a constant negative 1. So let's go ahead and maybe rewrite this a little cleaner. When I go to, we can distribute this term back into our parenthesis here, and we'll have some constants to combine. 2 and 3 would give me 6, and then e raised to the third and e raised to the fourth would give me e raised to the seventh, because I'm going to be adding those terms back together. I can do that same distribution for the e raised to the third. So we have negative 2e raised to, again, the 7th power. And then we'll have the next term. Again, this whole parenthesis was negative 1. So we get to the final result here. This will have a double negative when I'm done with these two. And so we'll just get 2e raised to the fourth. So positive 2e raised to the 4th power. And if we want to use our calculator to figure out that last bit, we can consider this approximate solution to be right around 4,495.73. So that would be our final result for that exponential result. So this just used, again, the product rule for exponentials to work this out. And we also used that previous result for the integral of x e to the x. The last few problems that we'll take a look at consider integrals where it's helpful to do multiple iterations of the integration by parts method. And this is sometimes called the tabular method or a table method. And I'll go ahead and show you guys how to set this up. So if we considered these functions, it looks like it's going to take a little bit for us to break this function, this cubic function, down to where it's kind of easy to take its antiderivative along with e raised to the negative x. So when I'm considering this, we'll call tabular method, we want to consider again our same two components, our u and our dv. And I want to choose again the same idea as for the u. I want a u function that starts to simplify as I take its derivative. The dv would have to be the other component of the function. So for this rule, I'm going to choose the polynomial here, 4x to the third minus 9x squared, and then the plus 7 as my u. And I'm just going to kind of list it down below, kind of like a column here. The dv ends up being just the e raised to the negative x term. And for this, I'm going to kind of leave off that dx term. We'll just kind of list the two components in the table. So for the left side, I'm going to consider, again, derivatives of this u function. And I'm going to take as many derivatives as it needs to get down to 0. So again, this method is only necessarily helpful when you have a u function that actually can be broken down to 0 when taking derivatives. So the first derivative here will give us a 12x squared minus 18x. We can take a second derivative below that as 24x minus 18. And then finally 24. And then last but not least, we can take its derivative to be 0. So it takes 4 derivatives here to get that original u function down to 0. I'm going to do the same idea for e raised to the negative x, but now I'm going to be taking antiderivatives. So when I consider the antiderivatives here, e raised to the negative x, well, this is an exponential term, so our antiderivative is going to be e raised to the negative x, and then we want to consider dividing by the derivative of the exponent. So if I divide by the derivative of the exponent here, that would be negative 1. So dividing by negative 1 would be really the same thing as multiplying by negative 1. So that would just give us a negative e raised to the negative x for its antiderivative. As we go for the antiderivative coming next, we still have e raised to the negative x. And if I divide again by the derivative of the exponent, that's still negative 1. Dividing this by negative 1 actually just turns this to a positive e raised to the negative x again. And this pattern actually will continue as I take these antiderivatives. So the next time will be negative, and then the final time it's a positive e raised to the negative x for those antiderivatives going back down. The other component that I'm going to consider here is the sign of each of these terms. When I go through kind of multiple iterations of our integration by parts, notice that in the original formula we have again the uv product minus the integral of v du. So each of the terms that I go through, the first would be positive, the second is going to be negative, and then that pattern will continue again over and over again. So to model that same pattern of a positive and then a negative term, we're going to label each of these columns or rows here positive, negative, negative, and then finally positive. And again, this is going to model the pattern that we're seeing in the integration by parts, where we have a positive result and negative term, and then that pattern will continue throughout. All right. So again, kind of playing off the original way that we work our arrows, the first is going to be a u dv product, which we're going to have a kind of arrow going diagonally first. And we're actually going to continue these diagonal pattern and these diagonal products until the very end of our row. So in this case, since we had to take 4 derivatives, we'll have 4 products here for this result. And those products will have the designated sign on the left side. So in this case, first term will be positive, and we'll start with 4x to the third minus 9x squared plus 7 times the exponential, and I'm going to just tack this on the front, negative e raised to the negative x. So that's term number 1. We have term number 2 that's going to be negative. So this would be negative. We'll have, again, a e raised to the negative x term. And we have our 12x squared minus 18x. So the product there is going to be negative still, since we have a positive product, and then we need to tack on our negative sign. The next component is going to be, again, plus 24x minus 18, and then times negative or minus e raised to the negative x. So this term will also have a negative e raised to the negative x, and we'll have a 24x minus 18. And then we'll have one more product to work with. We'll do that in purple. Negative 24 e raised to the negative x. So negative 24, and then e raised to the negative x. And like all of our antiderivatives here, we will have to, again, tack on a plus constant c. So that would be the final antiderivative there for that function. There is a second problem here, and for this one, I'll encourage you guys to maybe pause the video at this point, and you can go ahead and consider walking through this one on your own. And after we pause this video and come back, we'll take a look at the solution for this problem. Again, you're going to be using that same tabular method. Consider making your column of the u function and the dv function, and taking your products for those. All right, so if we were able to get these columns, that is great. We should have a u column and a dv column worked out here. The u column just has all of our derivatives of the u function. It looks like we had to take 3 derivatives to get down to 0. And then we have the antiderivatives for our e raised to the 2x. So in this case, we're dividing by the derivative of the exponent each time, which happens to be 2. So it goes, that denominator increases 2, 4, and then finally 8 at the very end. So when we take the products here with those arrows, we have 3 products to make here. The first is going to be positive. We'll have 2x squared plus 5x times the exponential e raised to the 2x over 2. The second product we'll see is going to be our negative 4x plus 5, and then we'll have e raised to the 2x over 4. And then the final product works out as positive, and then we'll have 4e raised to the 2x over 8, which certainly here we can just reduce down to a half if you prefer. And then we can add our final plus constant c. So there is our final result for that part I. So thanks for tuning in and watching our video here. Look forward to walking through the last couple sections with you guys. So I'll see you in the next one.